Hi, I'm Arel Anaya, and today I'll be presenting on the evolution of terrain relative navigation on Mars. So first of all, it's just a table of contents. I'll be going over the mission context for this technology. I'll then dive into what TRN actually is, why it was necessary. Then we'll talk about its evolution, how the control system kind of functioned, and then the future evolutions. How it's gonna progress as we advance our technology. So first of all, some mission context. I'm going to be talking specifically about the Perseverance rover and even more specifically a technology called Terrain Relative Navigation, or TRN. Perseverance landed on Mars in February 2021 in a place called Jezero Crater, and what I want to focus on isn't just the rover itself, but this one specific subsystem that made the landing possible in the first place. Because honestly, without it, Jezero wouldn't have even been possible as a landing site for this mission. So what is TRN? At its core, it's a guidance system that runs during the final minutes of landing completely on its own, no human input. Here's how it works. As the rover is descending, a camera called the Lander Vision System starts capturing images of the terrain below at around 4,200 feet up. These images get compared in real time to a map that was preloaded before launch, a map of Jezero crater, and that had literally thousands of hazard zones already tagged from orbital photos beforehand. If the system sees that it's heading towards one of those zones, it sends a correction command to steer away. The whole process takes about 50 seconds. And the reason that this all has to be fully autonomous, the reason that there was no other option to try to introduce some sort of human in the loop, is that the one-way signal delay between Earth and Mars at that point was around 11 minutes. By the time any command from Earth arrived, the rotor would have already landed whether we wanted it to or not. So we had to have a robust enough system that would be able to prevent us from crash landing, kind of guide us through that process. So why did this matter so much? Jezero Crater has been on scientists' radar for a long time. It's a fossilized river delta, one of the most promising places on Mars to look for signs of ancient life. But it is also considered too dangerous to attempt a landing there because of how rocky and uneven the terrain is. And that was actually a reoccurring problem throughout the history of Mars's exploration. Mission planners kept having to choose between landing sites based on what was safe, not what was actually scientifically interesting for us to study. Flat, boring terrain was always the safer bet. TRN kind of helped us break free of this pattern. It's what made Jezero viable. And again, the autonomous piece isn't just a fun little engineering feature, it was a hard requirement for this type of mission. You cannot remote control a landing to Mars in real time. The physics of the signal delay just don't allow it. We are far too limited, so we have to design these systems that are going to be able to allow us to even get the chance to explore these types of terrains that are much more interesting for scientists to study. So here's kind of a quick timeline. Pay no attention to the symbols. This is just a fun template. I don't think we had AI in 1976, but to really understand what TRN achieved, it helps to look at how Mars landing evolved over time. Viking, back in 1976, used basic radar altimetry. There was no hazard avoidance. You put the site from orbit, hope for the best, and committed to that. Pathfinder in 97 used airbags. The rover basically bounced to a stop whenever it happened to land. Spirit and Opportunity in 2004 added retro rockets to slow the descent, but you were still looking at landing ellipses of around 80 kilometers, meaning the rover could end up anywhere within that 80-kilometer area. Then Curiosity in 2012 introduced the Sky Crane, which was a huge deal mechanically. But here's the thing. From a control standpoint, Curiosity's sky train was still open loop. It flew a pre-planned trajectory, and that was it. No corrections, no feedback. Perseverance used the exact same sky train hardware. The difference is that Perseverance kind of closed that loop in terms of controls. It added real-time feedback on top of the same system. It was still the same train, but it was kind of fundamentally under a different guidance. That's kind of what allowed us to jump from Curiosity to Perseverance and have this better system. So speaking of the actual control system, it is essentially a state estimation and feedback control problem. The rover is coming down at roughly 100 meters per second. During the descent, the system is matching visual features from the camera image against a preloaded map to estimate where it is laterally, how far off course it is relative to the target. That position error becomes the input to the control law, which is then going to drive correction commands to the lateral thrusters. There's also a hard time constraint. The system has to make its corrections before about 1,000 feet altitude, because below that there just isn't enough time or room to maneuver, and there's a fallback built in. If the image matching isn't confident enough, if the system isn't sure what it sees, it doesn't guess. It would default back to the pre-planned safe landing target, which is kind of exactly what you want from a well-designed control system. In these types of missions, we're trying to gather as much scientific research as possible, but we also don't want the mission to fail due to just the amount of work and funding that went into it. When the control system is uncertain, you don't want it to take risks. You want it to be able to fall back to some sort of conservative option that still would allow us to continue the mission. Talking about the future evolution for this project, kind of where does this go from here? TRN on Perseverance got to about 40 meters of precision, which was a massive leap forward from Curiosity. But future missions are going to need a lot more than that. The Mars Sample Return Lander, for example, needs to touch down within roughly 1 meter of the sample tubes that Perseverance attached on the surface. That's a 40 times improvement in precision over where we are now. To get there, future systems will probably layer in LiDAR kind of giving them that depth sensing on top of the camera-based matching, and eventually pull in signals from proposed Mars navigation satellites. Basically, a GPS equivalent for Mars. For crewed missions, the bar gets even higher. Astronauts need to land close enough to pre-positioned supply depots to actually reach them. So at that point, the guidance system isn't just some sort of achievement. People's lives will start to depend on how accurately and how closely we're able to get to these landing sites. And longer term, the vision is to move away from pre-designed landing targets entirely. Instead of the spacecraft crafting a target that humans pick from Earth, the system would assess terrain in real time and choose the best spot on its own. This shifts the problem from reference tracking to just a full-on autonomous optimization. And while that's probably still a decade or two out, TRN on Perseverance was the first step towards that direction. And these are my sources. I pulled from NASA's JPL official EDL documentation, the Mars 2020 mission overview paper from the Space Science Reviews, the foundational TRN algorithm paper, and the NASA Lander Vision System fact sheet. Thanks for taking the time to listen. Goodbye.